Hello. In following two sections, we are dealing with partial derivatives, which is the way to take the derivative in R3, R4, and so on. So these are the derivatives of multiple dimensions. So first off, let's go back to Calc 1 and just write one thing. We have in R2, yes, with K's, of course, it's calc, it's not salts. So it's calculus 1, right? So what do I have? I have a function f of x. There we go. I have function f of x, so that is y equals f of x. And then we can take the derivative, right? We can denote as dy dx. We can also call it f prime, so those are all different notations for the derivative. There are more. Now, what that was the slope of the tangent line. So if I pick a maximum point over here, we would have the horizontal. That was terrible. So this would be horizontal tangent line whose slope m is equal to f prime computed at a. That will be the a value. We can also come up with any other point, and the tangent line would be going through that point, right? This is b, so in this case m equals f prime of b, and so on. So we can find the derivative at any point, and what that derivative gives us is the slope of the tangent line, which shows the change of the function at the point, at the instant. So if you take the derivative, you can find the change of the function in that at that point. Now, what does that mean for calculus 3, where you have a surface, right? Well, if you think about the surfaces, so if you observe the images that are given to you in a textbook, which are nicely done, these are actually hyperbolic paraboloid images. You can see the north and east and the south and west, right, on those two hills, and the person trying to walk, right, up the hill. The derivative is going to give you the change in elevation of that hill. So the change in elevation, but it's only going to give you the elevation in the direction of the x-axis or in the direction of the y-axis. So if you are going to walk southeast or any degree off of these derivatives will not detect those changes, and we cannot measure those with partial derivatives. So now, what is this partial derivative? So if we set up some kind of a surface over here, this is some kind of a surface, it's wavy, it's all of that. And now I'm going to set up the coordinate system. Yes, I can. I don't want to. So just draw any kind of random surface, right? And I have this surface, and now what I'm going to do is on the surface here, I'm going to come up with some kind of the x path. So this is the x path, and in the blue, let's say right here, right, is the y path. Now this surface is above the coordinate system, right? The z. Actually, when I think better, this y path is supposed to cross the z-axis. There we go. Perfect. Right, there we go. All right. So now you have that the red path is above the x-axis. So now I can actually extend the x-axis this way, and I'm just going to try and see if we can somehow Can I maybe do this to say that that corresponds to, there we go. So this is what we have. This is the x path on the surface, and you have the x-axis underneath. So yes, x-axis is a straight line. The reason why the red line is wavy is because the surface is not flat. The surface is changing its elevation. So now, since this surface is changing elevation, if I am to find the derivative, let's say at this point, the derivative would give me a tangent line, and that would be two-dimensional now. So when you are looking for partial derivatives, you are effectively killing one of the dimensions in the input. So if I'm looking for the partial derivative in respect to x, I just ignore y. I keep y constant. And because y is kept constant, the partial derivative in respect to x is only going to measure the change in height, elevation, or whatever we are dealing with, temperature. Right? It's only going to measure the change in x direction. And the same thing is going to happen with y direction. So if I am to extend the y-axis and then make these guys, right, go down like this, then what I have here is something that would measure the change in y direction. So now I would draw a tangent line, let's say here. Again, horizontal tangency, this is a local maximum right there, right? And this would be only the x path. So now here, this m would be what we call the partial derivative, and the partial derivative of y. So we see f subscript y, and the red one would be m equals partial derivative of x. So partial derivative measures the change along x-axis, that would be partial derivative with respect to x, or y-axis, which would be partial derivative with respect to y. So these are the two partial derivatives, and they measure the change only along those axes. Next, not next section, 2 sections from now, 12.6 is directional derivatives, and directional derivatives will measure the change in any direction. So right now we are only stuck with the derivatives in x direction and derivatives in y direction. So technically what we are doing is we are taking this third-dimensional space and we are reducing it down to 2-dimensional space where fx, partial derivative, is going to be the xz plane, and fy is the yz plane. Now each one of these is actually your good old Calculus 1 f prime derivative, because we are ignoring the rest of the input that you have. To find the partial derivative, as I said, the mechanics of it should be very easy. If you are looking for partial derivative in respect to x, you ignore y's. You keep y a constant, and which would kill all y terms. If you just have y squared and you are taking derivative in respect to x, well, it's 0, right? And then you do the same thing for partial derivative in respect to y. You keep x's constant. Now, the derivation for each one of these is absolutely identical to Calculus 1 derivation. So we have the same definition that we had in Calculus 1 with the limit of h goes to 0 of f of x plus h and so on, except now we just have to say comma y for each one of those. So the standard definition for the partial derivatives would be that fx, right, the partial derivative in respect to x, also denoted as partial f partial x. This symbol is partial derivative. So it is some kind of curly d, right? You have your regular d for derivative, and then you have the curly d for partial derivative. So we denote with f subscript x, that's a small x in the corner, and or you can use the Leibniz notation, which is partial derivative of f in respect to x. And the definition for this would be the limit as age goes to 0. And now you have your good old f of x plus age comma y, right? Because your input is two-dimensional, but we only are worrying about the change in x because we are looking for the derivative in respect to x, minus f of xy divided by age. So as you can see, if you are to erase all of the y's for this definition, it will be identical to the calculus 1. And now you have one for y, where this age is going to impact the y direction. So partial f partial y is the limit of age goes to 0 of f of x comma y plus age minus f of x y divided by age. So these are the limit definitions of the derivative for partial derivatives. And to derive these, you would do exactly what was done in calculus 1. Except every time you write f of x, you have to write f of x comma y, and then it's plus age and all of that stuff. So now that we have the definition for the derivative, this is the official definition, now we can go back and deal with calculation. Now, calculation, as I said, for partial derivative of x, keep y a constant. So some terms will completely be gone because they will only have y. So if I have f of xy, which is our function, to be 3xy squared minus 4 sine y plus 3, if I look for partial derivative in respect to x, the only term that I have to consider is the first term, because that's the only term that has x's. So derivative is 3y squared. The rest, the other two terms die because they're constant in respect to x. There are no x's in these terms, so they're both gone. Now fy, for the same problem, fy is going to consider the first two terms because they have y, and the last term is going to be gone because it's just constant. So now if I'm taking the derivative in respect to y, the derivative of y squared is 2y, so this is 6xy, very good, minus, and now derivative of sine is cosine, so we have 4 cosine y, and then it's still plus 0 for that 3. So what I've seen in the past in the adjustment that you have to make is you are used to, maybe it evaporated by now, I don't know. From calculus 1, you are used to, when you take the derivative of y, you follow it with the chain rule dy dx, right, for implicit differentiation. Well, over here, no implicit differentiation. Y is as good as the input as x is, right? It's independent variable. Where in calculus 1, y was dependent variable. It depended on x. It was a function of x, which is why you had to use the chain rule for implicit differentiation. Now, you are only considering each of the dimensions of the input, x and y. They're the same. They're the same, and you will be looking for the derivative in respect to one or the other. So there is no implicit chain rule happening in this case. So f of x, y, you can exploit the symmetry of the problem. So for instance, if you have a square root of, let's say, 4xy minus 9, the derivative in respect to x and respect to y in this problem are going to be the same, because And this is what we call a symmetric problem. See, the upper problem ruins the symmetry with a square over here and no x in this term. It should be xy or something like that, or another sine x. So if the problem looks, if the derivative of this problem looks the same, then we call it a symmetric problem. Let's take a look. So fx is equal to the derivative of this. We know that the derivative of square root of x is 1 over 2 root x. Now that has to stay, right? So this is going to be 1 over 2 square root of 4xy minus 9. And then the derivative goes on top, the derivative of the inside, right, because of the Calc1 chain rule, and that would be 4y. If I find the derivative in respect to y, well, it's going to be the same thing. You have 4xy minus 9, and you will have 4x on the top. So this is when I say what the problem is symmetric. You take a look at their derivatives look the same, right? Except you have 4x and the other one has 4y. So you are dealing with the calculus 1 derivatives where you are ignoring one of the two dimensions, right? Whatever derivative you're looking for, you are ignoring the other dimension as a variable. You're regarding it as a constant, and then you either copy it or you kill it if it's the only one in the term. So going back to the first problem, the first term has both dimensions, so the first term survived in both of the derivatives. The second term did not have x dimensions, so that term was not featured in the x derivative because it did not have x dimension for you to take the derivative of. F of xy is equal to, let's see, something cool. Y e to the x minus 3 ln xy. Observe that both of these terms have both dimensions x and y, which means both of these terms survive, right? The differentiation in both of the partial derivatives. So try these on your own, and then we'll take a look. So partial derivative in respect to x. Well, the first term stays the same because derivative of e to the x is e to the x and y is a constant. So the first term stays the same. The second term is going to be 3, you copy, and then the derivative of ln xy is going to be, we copy the function in denominator and take its derivative on top, right? The derivative of xy is just y because derivative of x is 1, and then y's would cancel. So the answer here is y e to the x minus 3 over x. Now, the partial derivative in respect to y, derivative of y is 1, so this is just e to the x, and then minus, and now we have the same thing happening here because, again, this is symmetric, right? It was ln xy. So it looks the same if you swap. What does it mean to be symmetric? If you swap x and y, you end up with the same function, right? So that's basically, and you know that the derivatives for those pieces would be the same. So this is just 3 over y, but let's do it. For ln, you write the function as is on the bottom, which is xy, and then its derivative on top. Derivative of this would be just x. Then x's cancel, and we have e to the x minus 3 over y. Let's take a look at some problems from the textbook. They have a lot of wonderful exercises over here. Ooh. Let's see. Function s of yz is defined as z squared tangent yz. What is the partial derivative sy and what is the partial derivative sz?